about now? Maybe? Yeah, that sounds better. Okay, yep. We'll be doing iClicker today, yep. Yeah, class still counts. And I'll know if you're not here because I'm the one that grades it. Okay, and again, quiz Monday, test next Monday. Any other questions? Yeah. They will be in here in person, multiple choice. You just come to class on that Monday and take the exam in here. Anything else? All right. So to get started, we left off last class talking about stoichiometric solutions, and we did this as an iClicker. So we will just go through this together just to finish off our discussion at the very end. So we talked about the balance of this, or the balancing of this equation. So we have sodium hydroxide, and we have H2SO4. And that's forming water, and that's forming sodium sulfate. And to balance this, you need 2 sodium hydroxides for every 1 mole of H2SO4. The thing to note here is that we now have a volume component and we have a molarity component or a concentration. So in order to get to moles of solution, we need to use the molarity of H2SO4, which is moles over liter. And we'll multiply this by the 20 milliliters, which is 0.02 liters of solution. And we get 0.0049 moles of H2SO4. Where this gets tricky with acids and bases is that we now have a 2-to-1 molar ratio for your base to your acid. So using the moles of your acid, you now need to use your stoichiometric coefficients in order to find how many moles of your sodium hydroxide you need. So it's not just a 1-to-1 here, it's a 2-to-1. For every 1 mole H2SO4, you have 2 moles of sodium hydroxide. So you need twice as much. Okay. And then in order to get back into molarity or concentration, right, because that's what, or in order to get the volume that we need to use that concentration of the sodium hydroxide that you have. So again, molarity is moles over liter. You're given moles, and so in order to cancel that out, you can say 1 over 0.0098. That'll give you 1 over liters. So then if you flip that, you'll end up with the 16.1 milliliters. All right, you can also write this as right, you can solve for it that way, and then this would all be to the -1. Okay, are there any questions using this one? If you have a 1-to-1, so 2 monoprotic, an acid and base, it's just going to be a 1-to-1, but when you have diprotic, which is the 2 H's, that's when this comes into play. Yep. Yeah, so if you solve it for the 0.61 moles over liter divided by the 0.0098, you'll end up with 1 over liter. So then you take it and you inverse it. And that'll end up with your liters and then convert to milliliters. Yep. Any other questions? All right. So let's look at this one to finish up our stoichiometric solutions. We have considered the reaction between 15 milliliters of 0.1 molar calcium nitrate and 25 milliliters of 0.005 molar ammonium phosphate. We want to write the molecular equation for this reaction, write the net ionic equation, and then how many grams of the precipitate are formed. Okay, so looking at A, what is our molecular reaction? We have calcium nitrate, calcium, NO3, 2. Calcium's a 2 plus, nitrate's a -1. And then we have ammonium, which is NH4 plus. And we're going to need 3 of those because we have the phosphate ion as well. Both of these are aqueous. What forms? Ammonium nitrate. Is that aqueous or solid? Anyone know? This is going to be aqueous. And what is the other, or what is the other product? Calcium phosphate. And I will tell you that this is solid. Okay, so which one's your precipitate? Calcium phosphate. Yep. Is this reaction balanced? Nope. Quickly balance it. You can work with the person next to you. Alrighty, what goes in front of the calcium nitrate? 3. What goes in front of the ammonium phosphate? 2. What goes in front of the ammonium nitrate? 6. What goes in front of the calcium phosphate? Nothing. Keeps a 1. Perfect. If we were to write the net ionic equation, we have to break everything apart into its ions. That's a lot. We're not going to go through that. Prove that to yourself that you can do it. And your balanced calcium, or your balanced net ionic equation is calcium 2 plus the phosphate ion, forming your precipitate. Your everything will split on your reactant side. The ammonium nitrate will split on your product side. You'll keep your product of the calcium phosphate. That precipitate will stay solid. Your ammoniums and your nitrates will cancel out in your complete ionic equation, but your net is going to be just the calcium and the phosphate forming the precipitate. Then for C, how many grams of the precipitate are formed? How can we get to this? What do we need to get to first? What unit? We need our moles first. How are we going to get to moles? We can use our volume in our molarity. What are we given for both of them? Are we given molarity and are we given volume for both of them? Yes. So what do we need to find first? We need to find our limiting reactant, correct? Right? So in order to find our limiting reactant, we're going to take 0.01 molar calcium nitrate Sorry, just pretend that this is 0.1. Sorry, 0.015 liters is what that's supposed to be multiplied by. And we end up with 0.0015 moles of calcium nitrate. And we're going to do the same thing for our ammonium phosphate. Okay. Once we are in moles, how do we find our limiting reactant? What's the shortcut we learned? We need to divide by our coefficient. So we're going to divide calcium nitrate by what? 3, and divide our ammonium phosphate by 2. Which one's our limiting reactant? Calcium nitrate is our limiting reactant. Okay, now we don't use that 0.0005 again, right? This is just to tell us this is our limiting reactant. We don't care about it. We still need to use this many moles, the 0.00015 moles. How are we going to get to grams? We need to use our molar mass. What else do we need to use? Our ratios as well, right? So you can prove that to yourself moving forward. You'll have 2 moles of your, not 2 moles, 1 mole, excuse me. Just 1 mole. 1 mole of your calcium phosphate. And then for every 3 moles of your calcium nitrate. And then you'll use your molar mass and solve for it there. And you can prove the rest to yourself. This is where molar mass goes. Okay. Any questions on why we needed to solve for the limiting reagent first? Okay. Anytime you're given a question and you have the concentration of both reactants in your chemical equation, that wants to be like a trigger that says I must solve for the limiting reactant because I don't know how much could be produced. I have to see what my least amount of moles is first. All right. Great. Okay, so with that, we're going to move on to our next unit. Our next unit is going to be gases. So there's a couple things that we're going to talk about with gases. We want to describe the property of gas. We're going to convert between different pressures. We're going to determine or define the term absolute temperature. Convert between Celsius and Kelvin, right? So that's where that meme came from in the beginning. We're going to describe the relationship between different conditions, so volume, pressure, temperature, moles, and we're going to predict the volume based on a change in pressure. Right, so a couple things about gases is that gases do not have definite volume or definite shape, right? A gas is filling this room right now, but if we scrunch this room down, it would still fill that shape. Depending on the space that it's in, that gas will fill that shape. Gases have very low densities, and the densities will vary with changing conditions. And gases mix with one another readily, right? Think about the oxygen and the air that you're breathing. There's a whole mixture of gases. And gases change volume dramatically with changing temperature. So at higher temperature, gas moves more quickly. Right? And if you think about this, if you're going to boil water, when you first start boiling water, you don't have a lot of gas bubbles. But once you get that heat going, your bubbles are moving faster, right? And the faster those are moving, it's because they have more energy associated with them, and that's due to the higher temperature that they have. Alrighty. So there's two different equations that we're looking at here. We're looking at the force, which is gravity, and its mass. You might remember that from physics. And then we're also looking at pressure, which is the force divided by the area. Right, so using that gravity times mass, and then using that area formula as well. So if these two cylinders have the same mass, which one will exert more pressure on the surrounding or on the supporting surface? What's the difference between these two? The diameter of the circle, right? It's a cylinder. It's going to be dependent on that diameter. So which one would you expect to have more pressure? The smaller one, right? Smaller area. So when we look at units of pressure, there's different pressure units that we can look at. Most of the time, your units are going to be in atmosphere. However, we see a lot of them in millimeters of mercury or in torr. And all of these conversions will be given to you on a sheet if needed. But this is a good slide to reference in case you need to convert anything with your homework or with just regular questions before an exam. Okay, and this is all just showing that the atmospheric pressure will push up and into the cylinder as much as it can, right? There's more space above the atmospheric pressure, so it's not filling it all the way, but we fill it up all the way that we can with the atmospheric pressure pushing down. Right, and we can convert between all of these, and this will show you what that atmospheric pressure is. Okay, so talking about a gas, there are 4 different states of the gas that we can talk about. We can have the pressure, so this is how the gas particles are hitting the container that it's in, right? So if these are moving, these will hit the walls against it. We can have the volume, right? The space that this gas is taking up. The temperature, how much energy do those gases have? And then the moles, how much of that gas do we have? Any 3 of these properties identifies the state of the gas. So if you know the 3, you know what it's doing. These can be held constant, these can change, and we're going to talk about the different properties that change once these are changing. Right, so the pressure exerted by a gas is related to the frequency of the collisions between gas molecules and the container walls. So if the gas molecule is hitting the container faster, that means it's going to have more pressure. But if there's less collisions with the wall, that is less pressure built up. So if you think about a balloon, right, if you only have a couple of gas particles in there, it might be very deflated, but the more air you put into it, the more gas particles you have, the more pressure it has, the bigger it gets. Alrighty, so let's try this first clicker. What happens to the pressure in the container when the volume is decreased? Your temperature and your moles are constant. So the only thing that's changing is the volume, and how does pressure change from there? Give y'all like 30 more seconds. Okay, we'll close it there. Okay, great. It increases. This is correct. Right, this should go up. If we're thinking about a gas particle, right, if we think about, oh, don't. Sorry. I won't grade that one. Right, so if we're thinking about gas, if we think about the gas that's in a basketball, right, it has so much pressure in that basketball at the time. It has a certain amount of gas particles, it has a certain number of moles, and it's at a certain temperature. If we just try to squish that basketball down to the shape of a softball, say, now those gas particles are in closer proximity, so they're going to be hitting the walls of that shape more frequently, increasing the pressure. So as volume goes down, pressure goes up. Right? So what kind of relationship is this? It's an inverse relationship. Awesome. Right? And so that relates, and there's a name for this. It's called Boyle's law. And this is looking at the pressure and volume are inversely proportional. So if we look at T, or if we look at volume 1, right, we have a larger volume here, and we're going to shrink our volume to volume 2. When we see that pressure goes from 1 to 2. So as we probably have our volume, we're increasing our pressure by 2. Right, so pressure is inversely proportional to volume, and the pressure times volume will always equal a constant, assuming that temperature and number of moles are held constant. So if you change one pressure and volume and you change one of those conditions, then we're going to have P2V2. So kind of think of this like when you're doing a dilution, right? We know M1V1 is equal to M2V2. It's very similar here, but now we're looking at pressure and volume instead of molarity and volume. When you do lab, you will do all of these so you can prove to yourself that pressure and volume are inversely related. Okay, so now let's do this question. Let's put it into action. A sample of gas occupies 5.8 liters at 1 atm. What is the pressure of a sample if the volume is increased to 9.65 liters? Before we even begin, what is happening to our volume? It's increasing. So what should we expect the pressure to do? It should expect to decrease. Okay. I'll give you like a minute and a half for this one. It'll give you like 15 more seconds. We had like 2:30 last time. Okay. We'll stop here. What's our answer? Yeah, awesome. It should be A. Okay, great. No one picked B or C. Awesome. Right, so again, this is a really good test taking strategy. Right, we expected our pressure to go down, right? If we look at P1, V1 equal to P2, V2. Our volume went up, so we expected our pressure to go down. So B and C do not make any sense. You can automatically decrease those, or decrease. You can automatically get rid of those. So if we're going to plug this in, we'll have 5.8 liters times 1.0 ATM. And that's going to be equal to your X times your new volume, which is 9.65 liters. And so if you solve for X, we get 0.61 or 601 ATM, which is A. Any questions on Boyle's law? Okay. Right, so that's for pressure and volume, but we can also talk about the volume and the temperature. So the speed of the molecules in a sample of gas is proportional to temperature. So what happens to the volume of a balloon when the balloon is cooled, right? The temperature is getting lower. What do we expect to happen? We'll do this clicker question. Right, this time pressure is held constant, so we need to maintain that pressure, and the moles are held constant. So what's going to happen as the volume or as the temperature goes down? Think about a balloon in this case. I'll give you like a minute from here, unless everyone answers real quick. Okay, we'll give you like 10 more seconds. Last couple people get your answers in. Okay. What's our answer? What happens to our volume as temperature goes down? It decreases. Awesome. Great job. Perfect. Right? And so if we think about this way, right? As temp increases, what happens to our gas particles? What do they need to do? They need to expand, right? They're getting bigger, so volume goes up. So in the same sense, if temperature is decreasing, that means that your volume needs to decrease as well. As temperature is going down, your particles aren't moving as fast. And so in order to maintain that same pressure, we need to decrease that volume so your particles are hitting the sides of the walls faster, or not faster, at the same frequency as which they were when they were at that higher temperature. Okay? The temperature is related to the kinetic energy, which is related to how fast that particle is moving. So if they're decreasing their kinetic energy, you need to decrease that volume as well. Alrighty, so here the volume and temperature is known as Charles' law, and the volume and absolute temperature T are directly proportional. Does anyone know what absolute temperature means? Yeah, this is your Kelvin scale. So your Kelvin scale is known as absolute temperature, as the absolute temperature scale. So it's used for all gas laws calculations. So you always want to take 273.15 plus your degrees Celsius in order to get into Kelvin. So this means at 0 Kelvin or absolute zero, right, we have no motion. That particle is still, there's nothing associated with it. It has no energy. It's not taking up volume. It's not doing any of that. Okay, so we can see here that between our Celsius scale and our Kelvin scale, these are the same component, or these are the same volumes, right? This is 40 and this is 40. However, they're just on a different scale. With gas laws, you must convert to Kelvin for all gas law calculations. You're going to be multiplying and dividing, but you're adding 273, so that's not going to be the same relationship between them if you solve for it using Celsius. Okay. And the thing to note here is that V over T in this case is constant. So if temperature is going up and volume is going up, oops, undo. And your volume is going up, what kind of relationship is that? Directly proportional, right? Directly proportional relationship. So what did we say? Boyle's law was what kind of relationship? Inverse. And what about Charles' law? Direct. All right, let's talk about one more. Or we'll practice this real quick. And so then the same thing can be said, sorry. You can say that they are equal to each other. So same like M1, V1 this time, except now we have V1 and T1 equal to V2 over T2. And this is just a fraction rather than two things being multiplied. All right, so a balloon originally had a volume of 4.39 liters at 44 degrees Celsius and a pressure of 729 torr. And the balloon must be cooled to what temperature to reduce its volume to 3.78 liters? We're going to stay at constant pressure. So do we need to do anything with our pressure unit? Nope. And then our volume is doing what? Is it increasing or decreasing? Decreasing. So what do we expect our temperature to do? Temperature is also decreasing. Perfect. So let's solve for that calculation as well. What unit is your temperature in? It's in Celsius. What do you need to do? Convert it to Kelvin. Mm-hmm. Mm-hmm. Okay, we'll give you like 30 more seconds. Notice what units your answer choices are in. What do you have to do once you find your temperature? Hint, hint. Okay, last final answers. Lost someone. All right. Oh, gained someone actually. Okay, what's our answer? Oh, okay, let's talk about it. We'll repoll. Alrighty, so the first thing you needed to do was convert to Kelvin. And then you have volume 1 over temperature 1 equal to volume 2 over temperature 2. What's your first volume? 4.39. What's your first temperature? Yep, so 317 Kelvin. What's your second volume? 3.78. And your X is going to be your temperature 2. So we get X equal to about 273 if you solve for it. But what unit is this in? Kelvin. What are our answer choices in? Celsius. So let's repoll. You get 30 seconds for this one. I know there's a couple more of you. Put your answers in. Okay, I'm going to stop in 3 seconds. That looks a lot better. Great. Okay, so your answer choice is D here. Are there any questions on when to convert to Kelvin, how to convert it? No? It's very important. It changes your whole answer if you don't. All right, there's one more relationship that we can talk about that relates some state of your gas to its volume, and that's going to be the volume and the moles. So if we have a certain volume that we're looking at and pressure is staying the same and temperature is staying the same, what happens if we put more moles of a gas added to that system, right? We want to keep pressure the same and temperature the same. So if we're putting more moles in our system, we're going to get more collisions. So what's going to happen to our volume? Give you 1 minute for this one. All right, you're putting more moles in your system. What's happening? Okay, we'll give you 15 seconds. Unless all my people put their answers in. Okay, we'll stop here. So if we're putting more moles of gas into the system, what's happening to our volume? It's going to increase. Awesome, right? You will increase your volume the more moles you have in your system, right? And if you think about this, if we put more moles in our system, that means that the pressure is going to be higher if we kept that volume the same. But in order to keep pressure constant, we need to expand it so that those collisions with the wall happen less frequently. So we need to expand our volume for the more moles that are in our system. And this is related to known as Avogadro's law. So the moles and volume are directly proportional. So as your volume increases, the number of moles also has to increase, or if the number of moles increases, the volume has to increase. So the more moles in your system, right, the bigger the volume it has to get. Right, so think about a balloon. The more air you're pushing into the balloon, the bigger that balloon expands. This is for constant temperature and pressure. So this looks very similar to Charles's law, where you have volume over pressure or volume over temperature, but this time it's volume over moles. Okay, so those three different laws that we talked about, Boyle's, Charles, and Avogadro's, all relate volume to either the moles, the temperature, or the pressure. When we look at this, we can rearrange this so that, or we can say that when volume increases, that means that the number of moles and the temperature has to increase, and that means that the pressure has to decrease, right? You can all see that way. We can take our volume equal to NT over P. And if the number of moles is staying the same, that means that pressure times volume divided by temperature would equal the number of moles. And if the number of moles is staying the same, this now turns into a constant. So now if the number of moles is staying the same and that's a constant, we can change all three states of our gas. We can change the pressure, volume, and the temperature of our gas. So now this becomes P1 V1 over T1 equal to P2 V2 over T2. This is known as the combined gas law. And this is for when number of moles is constant. Okay. And if you're looking for, like Boyle's law and Charles' law, you can see that Boyle's law is right here. And then you can see that Charles, his law is right here. Okay, so if you just remember the combined gas law, you still have all of your other gas laws or the broken down gas laws in your system as well. Questions? Right. Okay, so what happens to the volume of a gas in a container if you double the pressure while increasing the temperature by a factor of 2? Okay. Are we changing the number of moles here? No. So can we apply our combined gas law? Yes, we can. Okay, let's try this one.
And so you might want to say that we're increasing the temperature in Kelvin by a factor.
Okay. So it is implied, but this temperature is in Kelvin, right? Kelvin times 2. Whatever that temperature is in Kelvin times 2. Okay, we'll give you like 20 more seconds. Okay, we will stop here. Awesome job, guys, right? So it will remain the same. Awesome. And if we look at it here, right, pressure 1, pressure 2, right? We're doubling pressure 2. So that means that pressure 2 will be twice as much as pressure 1. And then we are increasing temperature by a factor of 2. So 2 times temperature 1 would be temperature 2. So if we plug that in, we get P1 V1 over T1 equal to 2 times P1 V2 over 2 times T1. Those will cancel out. So V2 is going to be the same as V1. So E remains the same. Okay. We will end this here today and we'll pick up with this small bubble on Monday. Have a great weekend. Yep.
What was the